we are bringing the same limit concept to another very important concept in calculus, which is called derivative. But before the definition and details, I just want to show you some daily activities which visualize actually the concept. For example, you see, like when we grow a seed, the seed actually takes some time. So with the passage of time, the seed grows up and then become bigger and bigger and bigger with the passage of time. Meaning to say, there is a change from the beginning state to the new state after some time. Okay, so at the very beginning it was just a seed, then after that it grown up and then was very very tiny seedling, and after that it become it created a small stem and then grow up, and then after that some leaves. So meaning to say, there is the main focus is in this example that some in our daily life there are many things and many aspects of our life that change occurs in some time. Okay, so actually the main focus is to evaluate the change, but okay, let's understand the phenomena first, then we will go in further detail. Like you see, with the passage of time the plant grows. So when the plant grows, actually it needs some time to grow. Okay, next example, you see, for example, you see the car is covering some distance. Okay, but let's suppose, for example, from the point from this point, okay, from this point to this point, when the car, you see, this is actually the change in the distance. Okay, the change in position. Okay, so when the car covers this distance, it takes some time. Okay, so the change in velocity uh, after some time, the same like these plants takes time to grow. So there are many phenomena in our life that it takes time, and with respect to the time there is some change comes in, but the change is not necessary that it must always be increasing. It may decrease also, decrease or increase, but there is a change with respect to time. Like for example, this one, if there is some business and the business is running very nicely, okay, and beneficial, so you see, with the passage of time the business the profit of the business is increasing. So you see, there is a change in profit with respect to the time. Okay, so you see, like this one, that with the passage of time, yeah, we cover this one, and with the passage of time, the car covers the distance. And now you see, if let's suppose from the beginning of the semester to the end of the semester, you see this beginning and end actually representing the time frame. So if some students continuously working hard, okay, from the beginning of the semester to the end of the semester, it will eventually change the CGPA. Okay, so the CGPA will be improved due to the change in hard work over some period of time. Okay, so the conclusion is something like this, that one entity is changing with another entity. For example, you see the plant grows, so the length of the plant or the height of the plant is changing with time. The CGPA is changing, okay, with the time. If you are working hard, so the CGPA will change. So this changing nature actually play a very important role, and this is our main topic today. Here is one concept. I think let me show you. Okay, the same changing nature I want to show you. There is one very nice example. So you see, this guy is standing here and looking at this balloon. Okay, this balloon. So the balloon will sometime with the passage of time, you see, the x component, this component show the time. Okay, from 0 to positive and towards negative, and this one show the y component, which actually represent at this moment the height of the balloon. Okay, so the balloon, you see, sometimes goes up, sometimes goes down. Okay, so how to calculate the change in the height with respect to the time? This is the main objective. So let me show you. You see, if you look at this, if you play this, click the play button, you see, with the passage of time there is a change in the height of the balloon. Okay, now if we visualize the average rate of change, you see, the average rate of change, that for example, from one point to another point, the height from one point to another point, and the time from one point to another point. Meaning to say, if you specify 2 points in the time axis and 2 points in the height axis, then that the relative change between those 2 points, we can say that the average rate of change, and it is also called average rate of ascent. Okay, so if the word ascent is not clear to you, don't worry, it means change. So what is it? It actually, the small triangle means change. Okay, delta. So this means change in height, you see, from here. So if let's suppose it is 148, let's suppose, so from 148 until this will be around about 190, something like that. So you see, from here to this point, this change divide by this change, when time was, let's suppose, 5, and now the time is, let's suppose, 18 or 17. So from 17 minus 5, you see h, you see this one, h2. This one, if we consider like 190, the height, this point, okay, and this one if we consider 148, So the value of change will be equal to, the value of change will be equal to 190 minus 148. This is just assumed values. So you will get some value. What could be the value? The value may be 2, and 8 minus 4 is 4. So 42. So 42 feet change from here to here. When this change was occurring, how much time it took to make this change? So the time it took was how much? You see, t2 minus t1. So the t2, if we just consider, let's suppose 18, okay, and the t1 is, let's suppose 5. So this will be 13 second. So in 13 second, the balloon from h1 to h2 reach, from this height to this height. When it was reaching, it took 13 seconds. Hello guys, is it clear? No?
Yes.
So we are at this point now. And this one, you see, if you play this play button, you see when there is a change in the x, there is a it result some change in the y axis also. And you see that the timing is actually showing here. Okay, if you want to check this one, show the secant line. The secant line is the line which connects the 2 points with each other. For example, here you see the height, the initial height, and then the new height. These 2 points, when you connect to each other, this line which connecting the change in the y coordinate is called secant line. Okay, and now change in height, h2 minus h1 divided by change in the time, will give us average rate of change. Is it okay? Hello? Okay guys, I will give you some time. Let me go through. Okay, you just see. You see, let me stop this one. The man stands on the cliff at the edge of the let's suppose of the rock, and watch the hot air balloon. Okay, so you can click. Okay, this one we already did. So when we click this one, and when we observe the behavior of this graph and the hot air balloon, there are some questions. You see, what is the average rate of change of the balloon's height between two different moments of time? Like you see, when you fix it, any moment of time, you just fix it. Okay, for example, if I just say that when the time is from 20 to 30, what is the change in the height? Okay, and what is the average change in height from when the time is from 20 to 30? So actually at that time you can assume and you can calculate. Okay, even you see the time we can drag. You see, when we drag the time to, yeah, it doesn't show, but maybe showing here. Yeah, I should fix the time to 20, yeah, time to 30. You see, we can fix here 30. You see, then we see the change on the height, in the height. Okay, so you can actually change the time, and with respect to the time, you will see the change in the height of the hot air balloon. So this is one question, that what is the average rate of change? You can fix any 2 point. Okay, any 2 point. You see, these both points are draggable. You can fix any 2 point between t1 and t2. Okay, and then after that you will realize the change in the height. Okay, so this is called average rate of. Now, what is the instantaneous rate of change of the hot air balloon height at a particular moment in the time? You see, these are a little bit different concept. One is called average rate of change, and the other one is called instantaneous rate of change. The instantaneous rate of change is actually the limit concept that we studied before. Okay, and what does it mean? It means that you see, when the change become closer and closer and closer to zero. You see, let's suppose the starting point is t1. Okay, and the change, which is t2, when the t2 goes closer and closer and closer to t1, so the more closer to t1 means actually the change in time is almost near to zero. Okay, so at that time, you see, at this time, what is the change in the height of the balloon? So that is called instantaneous rate of change. When we find the change in height at a particular point of time, when the time is very near or very close to zero. Okay, and that one we applying limit, so that is called instantaneous rate of change. See, if we on the secant line, okay, the secant line is connecting the change, the initial point and the later point. So the change, actually it shows when the line which connecting the 2 points in the y coordinate. So you see, when we increase, you see the secant line doesn't follow the blue line, the graph line. You see, sometime it doesn't follow. You see, it doesn't follow it, like it means that the green line doesn't fall straightly, like in the direction in which the blue line is. The secant line direction is also the same, but this will be the same if you drag the point 2 to closer and closer to t1. You see, at this moment, the more closer you are, the more the slope, okay, the 2 points, okay, actually it is also called slope, and the secant line will be very much fall on the graph. Okay, so it means that the instantaneous rate of change means that change in height at any particular point. Okay, for example, you see, average rate of change means that if something is going from here to here, and the time is t1 and t2. Okay, so if we divide the whole change in distance divided by the whole change in time, that is average one. But if we say no, we just want at this particular moment, at this point, I don't care before this, I don't care after this, I just want that what is the speed or the change at this particular point. This is called instantaneous rate of change. You see, in that case, you actually you no need to just change t2 only. If you want, you can change t1 also. Okay, you can bring t1 to any point that you want. Okay, and after that, if you want to change find the limit. Okay, the limit, then you can bring it. So there will be some point you see where it totally comes to zero. Totally come to zero. You see, the second line disappears. Why? It shows actually that if it totally becomes zero, then the limit, the function value will be undefined, and then the second line cannot exist. Okay, but we doesn't mean that it should be totally zero. No, it should be closer to zero. Closer to zero, not exactly zero. But the point when it closer to zero, if you look at the secant line behavior, actually it follow the graph. So the more smaller segment, you will get the more accurate value. Okay, so these are the two questions about this. And now you see, watch the animation. We already did that. Yeah, how go to this? Yeah, I think you can go through this by yourself. It is quite easy now. Now let's come to the definition of derivative. We saw the change in a graph, the change in the height of the balloon over some time interval. Okay, now let's connect this behavior with the definition of derivative. So what is it? You see, the rate of change is always considered with respect to change in the input value. The input value is actually the change in time. Okay, the input value. For example, the input value first time the t is, let's suppose the t is 5. So you see the 5 is one input. So this 5 will have some output here, let's suppose. Now the change in this input, the next input is, let's suppose, 10. So this will also have some output. Okay, so the change in input will generate some change in output. Okay, so the change in output divided by the change in input, this is called average rate of change. Okay, average rate of change. Now, after a particular fixed input value like 5 and 10, I already told you. So the foundation of the calculus is the instantaneous rate of change of the function. You see that the main, our focus today is actually the instantaneous rate of a change. So instantaneous rate is that particular moment when the change in the input value, like for example, previously I showed you 5 and 10. Now, if the change from 5 is very close to 5, like 5.00001, something like that. Okay, at that moment will be very closer to the change in the input value will be closer to 0, and then the change in the output value will be very accurate and precise. So how do we measure how fast a particular function is changing at a given point? Okay, so we can actually measure when we pick up any particular change in the input values. Okay, and then we will calculate the output values. So it may be like, for example, change in velocity, or maybe number of cells added to a bacteria culture per day. So you see there is gradual change, but at some particular moment, okay, what is the change? Or maybe what is the instantaneous change? Actually, we can find all these values. Okay, now the instantaneous rate of change may also be interpreted geometrically in connection to the function's graph, of course. And we saw the example. And this is the foundation to many of the main ideas in calculus. You see, in calculus in the future, you will see many all this type of derivative, okay, and differentiable words and equations. So like instantaneous velocity, a rate of change in speed over time. So instantaneous velocity is what? It is the rate of change in speed over time. So for example, if we for a function f, the average rate of change f, average rate of change of the function on the interval a. So first there the time was a, and after that there was another time a plus h. So from a until a plus h, there will be some change in time. Okay, so if these two values are given, a and a plus h, you can think like the a is time, t and t plus h. If the t and t plus h is given, okay, then we can see like this, that like average value of a comma a plus h, this will be equal to the change in speed. S represents the speed. From the higher speed minus the lower speed, you will get the average speed, and then this average speed was acquired in how much time divided by the h. Okay, so equivalently, if we want to consider the average rate of a change of a function on a comma b, you see here was a comma a plus h. So here is a comma b, no problem. Here the a plus h is just represented by b, so it's the same thing. So meaning to say the highest value minus the smaller point and the bigger time minus the smaller time, actually it will give you the average rate of change. Okay, now the average velocity at some particular moment is equal to instantaneous velocity. Okay, and the instantaneous rate of a change of a function at a point in terms of average rate of change of a function f over related interval, the instantaneous rate of change of a function at a at some particular point, like, okay, is called derivative of the function at a. Okay, now you see here in this example, if you say the instantaneous rate of change, and actually the instantaneous rate of change is we can calculate only when the change is very small. But you see, we can find out this change at this point. Now the change make it smaller. So this at this moment, what is the change? It is the change at this particular point is called derivative of the function at this value. Okay, in the same way, if you bring the t, let's suppose the t1, the t2 to this point, and the t1 to this point, and now make it again too smaller, you see here the change is in opposite direction. But again, what is the change at this particular moment? This is called the derivative of the function at this particular value. Okay, so this is called derivative of the function at some particular value. So the formal definition is like this, that let's suppose f be a function and x equal to a, this is the input value, is a value in the function domain. Function domain means it is the input value to this function. So we define the derivative of the function with respect to x, okay, evaluated at x equal to a. Okay, it is actually like this, that let's suppose you have a graph like this. So we have some function, okay, some function, and when we apply this function on any input value, let's suppose x, or maybe the input value we represent by a, or the input value we represent by t, whatever alphabet is it, but it means actually when the input value we represent by the x coordinate, so when we apply the function, this will give us some value in the y coordinate. Okay, now from this point to another point, if we find the average one, that is the average rate of change. But if we apply the limit, because you see when the change is very near to 0, it means very closer point to this, so here will be very closer change. This is called instantaneous rate of change, and this instantaneous rate of change is called derivative of the function at this particular point. And this particular point you may represent by a, or you may represent by t, or by h, by any value, but the derivative will be f prime, f dash, sometimes it is this is like f prime at a, or the derivative of the function at a. So you see, you just change the value of a if you want to calculate at this point. Okay, so at this point, what is the derivative? Okay, so at this point you will make a very small change, and here you will get the instantaneous change. So actually the derivative of this function at this particular moment, at this particular input value, is called derivative of the function, and it is represented mathematically like this. The derivative of a function is basically equal to limit h. The h is the change in the input value. You see here, when the change in the input value is very small, okay, almost near to 0, at that time the change in the y coordinate, you see this represent the y coordinate, the function f of a and f of a plus h. So the change here will represent the derivative of the function at that particular point that we want to calculate. So this is actually the basic definition of derivative. Okay, so we can try to find some basic points about derivative. That, for example, the derivative of function f at a particular value x equal to a, the x may be equal to a, x may be equal to b, x may be equal to t. But at this moment, if x equal to a is defined as the limit, you see the limit of average rate of change of the function on the time interval. So the time is first a, and then a plus h. So meaning to say from a the time change to a plus h, some change. But not the point, the change is that much smaller change that it almost equal to 0. So it is possible for, okay, this is also possible that at some time maybe the function value at the y coordinate doesn't exist. So if doesn't exist, then it means the limit doesn't exist. But if exists, if we get some value, then the limit exists. Okay, we also say that the function that has a derivative is the instantaneous change at x equal to a. So sometimes you don't confuse in these words. Sometimes it is called that this function is differentiable at the input value a. Okay, so derivative, instantaneous change, and differentiable, actually all these represent same quantity, same value. Okay, so next one, the derivative is a generalization of instantaneous velocity, or you can say instantaneous change of a position function. Okay, when if the y coordinate represent the speed over time. Okay, y equal to st means that the y represent the speed over time, is a position of the function of a moving body, and that we will represent by s prime a, tells us the instantaneous velocity of the body at that particular input time. So because if s measure the position in feet, so meaning to say in this point we are trying to find out the unit, the unit, what will be the unit of derivative. Okay, so from the previous point, if s is measured in feet and time is measured in second, then the unit of derivative will be what? Feet per second. Okay, so because the quantity f of a plus h minus f of a divided by h, this represents a slope. You know that the slope means the 2 points be the change. You see, if you have on y direction 2 points like this, and when you connect these 2 points, this line is called slope. Okay, this line is called slope. So this f of a plus h minus f of a represent the slope. Okay, through the line a and f of a, and the a plus h and f of a plus h. So then when we can compute the derivative at this particular point, okay, and of this slope, okay, thus the derivative itself represents the slope of a, particularly important line. Okay, so actually this line is very important, and it shows like this, that you see if we have the point a, okay, so here will be f of a, and here another new point will be a plus h, and here will be f of a plus h. The y coordinate, the y value is actually equal to f of a plus h. It should be a plus h. Okay, and here is a plus h, and here is a, and this one is f of a. Okay, so when you connect the f of a point with the f of a plus h, this line represents the slope. And when you find out at any particular point the instantaneous change, that instantaneous change is called derivative. And the derivative unit at this moment, if it is related to velocity, then it will be meter per second. Okay, actually these two values, you can say that the change, if you measure in whatever unit, that will be divided by the change in the input unit. So the output unit divided by the input unit. So this is the basic definition of derivative.